Hi everyone, my name is Akbar and this is an academic ZNotes live session on physics. And today I'm joined by published author Kaleem Akbar. We will be talking about refraction and total internal reflection. This is part one, so we'll be dealing with the concepts today, and on Thursday we'll be solving past paper questions. This is applicable to GCSE and IGCSE students for ages 14 to 16. All the resources and more past paper discussion videos are in the description below. Without further ado, let's get started. Hi, Kaleem, thank you for joining us.
Thank you very much again, Pugs, for the introduction. ZNotes, we are back again. And today we are indeed going over refraction and total internal reflection, topics that some might find quite difficult to get their head around. What I have got is a couple of practical videos that I would like to kind of share with ZNotes once they're edited that will allow you to see how this works. But for today, we're going to do the theory. And when I've finished editing the actual practical, I'll be giving it to ZNotes and Pugs, and they can do with it as they please. And you might just find it very, very useful to see what we're talking about rather than just talking about it. Because light is one of those abstract topics where someone tells you it's a transverse wave. What the hell is that? It vibrates 90 degrees to the direction of propagation. You're like, where? Have you ever seen light do this? So that isn't, funnily enough, today's topic. We are going to go into refraction and total internal reflection. So without further ado, let's get into it and let's unpack this topic. Now, first of all, refraction through a glass block. What is it? You might have experienced this as a young child yourself, okay, when you were amused by little things. If you take a pencil and you put it into a glass of water, all right, that's half filled, and you look at the pencil from the side, it looks like it's snapped in two. If you've ever been fishing, I've only done it once, I absolutely sucked. But if you've ever been fishing with someone who's really, really good, they even know wherever you see the fish in the water, that's not where it is. And I'm the physics teacher and I know the theory, but they know exactly where it is and can pull out fish after fish. So refraction is the bending of light. Now, I've got a cool party trick for you if you want to try, but please do it very, very safely. I used to love doing this with my students. I would take and I don't know where you're going to get one from, but please, I emphasize the word safely. I would, before my students came into a class, I'd have a big beaker full of vegetable oil. And what I would do is, before they'd walk in, I would have put a test tube into that vegetable oil and it would look completely invisible. You couldn't see the test tube inside the beaker. And then in front of them, I would take another test tube, much to the head of science distaste, and I would take in front of them, put the test tube in a paper towel, smash the test tube, which is always fun for a teacher. You never get to do that as a kid. Stick it into the beaker, and it looks like all the smashed glass disappears. And I do abracadabra, and if I could do the Harry Potter ones, I would. And I pull out the test tube that I had before. It's really, really cool. Should give it a go. And the reason that works is because the refractive index, which you're going to learn about today, the refractive index of the test tube and the refractive index of the oil are identical. And therefore, they bend equally. So the result of that is it looks like it's not even there, which is quite cool. So let us go into the actual theory of this. So on the right-hand side, guys, I've got this black ray of light. I know, but let's just humor me. So this black ray of light, and it goes straight through the glass. Shock. A ray of light goes straight through the glass. But this is highly examinable. See, what you might not know is right now in that orange glass, the light's slowing down. What you might not know is the wavelength is changing, but the one thing that stays the same is frequency. And I've got my own laser pointer here. Okay. Helium neon, red light, about 633 nanometers. It is monochromatic. Now, monochromatic basically means single color, although you're not allowed to call it that in the exam. Mono meaning one, chromatic, color. Monochromatic, as defined in the IGCSE and GCSE syllabus, is light of a single wavelength or single frequency. Now, I'm firing all these terms out. What the hell do they all mean? So let me get my drawing console up and give you an idea. Okay, so if I was to, oops, 1 second, let me just get this on. It falls asleep if I don't use it for a while. Here we go. So if I was to draw something like that, that is what you might call a really badly drawn wave. And the wavelength on that wave would be from one peak to the next peak, or from one trough to the next trough. All right. That's a symbol lambda. Lambda is a funny, like, kind of upside down Y, which is the symbol for wavelength. Now, we don't see time here, but let's just say that this was on some x-axis. Just, I'm going to keep it away for simplicity. And we've got 1, 2, 3, 4 full waves. All right, if I count off the end of the last one, let me just scrub that out. We have got 4 full waves. 1, 2, 3, 4. Yes, 4 waves. Now, if that was in 1 second, let's say the x-axis was 1 second, then the frequency of that wave is 4 hertz. Frequency is defined as the number of waves in 1 second. Wavelength is the length of one wave. Now, you don't see any of that when I draw that black line. We keep the whole thing simple by representing the wave as a single line. Now, why does the frequency stay the same? Because, you know, when students really think about this, it comes from the formula V equals F lambda. Highly, highly examinable formula, by the way. IGCSE Cambridge, I think I've counted in less than one hand how many times it didn't appear. Didn't. Okay, and that's like since 2002. So, look, if I told you, as a matter of fact, look, when light goes into glass, it slows down, then you're within your rights to think, well, to make this equation work, that means lambda gets less, or F gets less, or they both get less. But what we actually find is that doesn't change. If V goes down, lambda goes down, wavelength. And if V goes up, lambda goes up. And the reason for that is frequency is the number of waves in a second, guys, and it depends on the light source. See, this laser pointer doesn't care whether, not that it's got feelings, it doesn't care whether I shine it through glass, plastic, water, whatever. It gives out the same number of waves every single second. If you've ever watched these Hollywood films where, you know, they've got the machine that kind of throws out the baseball, all right, and then you're hitting it with a baseball. There's one of my favorites, Happy Gilmore. He wants to be a hockey player, and you know, he toughened himself up. He stands in front of this baseball machine, but let's just say the baseball bat. That machine does not care whether you hit the ball or not. That machine will still give out the same number of waves, or sorry, in this case, the same number of balls every minute, for example. That's what is meant by frequency. All right, so frequency won't change. Speed goes down because we're going into a more optically dense medium. In other words, we're going from air to glass. And the wavelength consequently changes. Maybe you've come across the experiment, which I'd love to, again, Pugs, share with you guys when the video is done, where you put white light into a triangular prism and you get all the colors of the rainbow, known as the visible spectrum: red, orange, yellow, green, blue, indigo, and violet. That's a very good experiment to show you that wavelength is changing. It's dispersing the light. It's changing white light into all of its component parts. Okay, so let me just get rid of, erase all this. And right, so wave slows down, but it's not bent due to entering along the normal. Now, what do we mean by that? Guys, the light is hitting the glass at 90 degrees. It's hitting it straight on, okay? Now, if you don't understand that right now, in the next couple of slides, you most certainly are. Whereas over here, we've got light hitting at an angle, and when it does, it changes direction. And that effect there is what we call refraction. When we go from a less dense medium into a more dense medium, light bends towards the normal. What do we mean by that? Well, look, guys, if the light was going straight, if I can keep this going, it'd be over here somewhere, but it doesn't. It bends in that direction. It's bending towards the dotted line. We say it bends towards the normal. Okay. Next, When it goes from more dense to less dense, it's now bending away from the normal. The incoming incident ray and the emerging ray are parallel to one another. Now, the angle of incidence is right in there. The angle of refraction is right in there. Incidence and refraction. Now, you might be wondering why there's two. We always treat each boundary on its own. So that's I. Okay, there's R. There's the next I. And there's the next R. Okay, let me just excuse me just a second. Okay, there we go. So IR. Angle of incidence does not equal angle of refraction. Okay, they are different. Angle of incidence equals angle of reflection, but they do not equal when it's angle of refraction. Angle of incidence, why do we call it that? Because that's where the light's coming from. Why do we call this refraction? Because that's where the light is going to and it's changing direction. Now that's for the first boundary from air to glass. Underneath, we've got another boundary from glass to air. And that's why we've now got a new angle of incidence I and a new angle of refraction R. Now look, you might think, but that I and that R are the same. They are, but they're not related. This I, incidence, is related to that refraction. This angle of incidence is related to this angle of refraction. Guys, I hope that makes sense. So moving on.
Just to add there,
yep.
That's because in the first case, you're moving from air to water, for example, and in the second case, you'll be moving from like water to air. So
absolutely, Pogs. It's all to do with. Now, if you're being geeky about this, it's called optical density, but let's just keep it simple for IGCSE and GCSE. In your head, simply think of solid, liquid, gas. It's a matter which one's the most dense, solid, then what, liquid, then what, gas. Now, the purists will argue that's incorrect, but I'll tell you, IGCSE, GCSE, and even A-level, you'll get passed with what I've just told you. All right? Now, that makes you think, oh, he's kind of lying to us. Well, it's one to help you, all right? It's just to make your life simpler. We don't need to make it more complicated at this stage than it needs to be, okay?
It's a good lie.
Well, it is. It is, and this is the thing. It's not that it's a lie. This is the thing. In general, this would be correct. It's like a bit like when we ignore air resistance. Well, does air resistance exist? Of course it does, right? But there are examples where it benefits us for ignoring it, okay? Like when you're dropping something from a small height. So it benefits us here to think of optical density as, just think of it as solid, liquid, and gas. Keep it nice and simple. So moving on. Right. Why does the ray of light change direction when it enters the glass at an angle? And, you know, this will also help you understand why it goes straight through when it hits dead ahead. Now, guys, I'm going to basically play this a few times, but we're going to kind of focus on this little go-kart, if you like, and we're going to watch the front right-hand tire. Because what's going to happen is when the front right-hand tire hits the mud, I want you to think of that as a more dense medium. See, all the other wheels will be in the road, okay? All the other wheels will be in the road.
All right.
And what will happen there is all those tires will be going fast and the front one is going to slow down, and that's what causes a change in direction. Watch this a few times and I'll talk over it. Watch a little diagram down the bottom and at the top at the same time. Pogs, I can hear some clicking in the background. Okay, so guys, what's going on here is when it hits the mud, the right-hand tire slows down first, and all the other tires are going very fast. So what happens is it changes direction, and then at the other end, it comes out first. So it's the one that speeds up first, and again, it changes direction. Now, if you imagine the car going directly at the mud, then both wheels would hit the mud at the same time at the front, which means it would slow down equally, which means it just passed straight through. But when you hit at an angle, there's always this change in direction. Guys, I hope that makes sense. Now, one of the examples I give to my students is, and this is going to be quite complex to explain without aids within a classroom, but let's just say, let me draw it here. Let me pause this. Let's just pretend, and my art's going to get tested here, which, by the way, if there was such a thing as Z minus, I would have got it. So let me just, oops, seem to have lost my pen. Let me go back and get it. There we go. So guys, I want you to pretend this is a beach. I know it says mud. Huh, my pen stopped writing. Why is that? Ah, there we go, we're back. No, we're not. Right, I'll tell you what I'll do on the previous slide. In fact, I'll do it on the next slide. Let's see if I can do it here. Bizarre. Okay, it's only happening in certain places. Let me just erase the ink. And what I'll do is I'll shelve it to a later on slide where I can draw. Okay, so let me just shelve it time being. In fact, maybe I can try to do something here to help you understand. So here we've got a glass block. We've got air, glass, air. Notice the yellow light is going straight through the glass. Why? Because it's hitting the glass at 90 degrees. Now look, let me use my pen, in fact. If I use my Apple pen here, if you imagine the light had wheels like a car, when it hits at 90 degrees, both parts of the wheels, the front wheels, would hit the glass at exactly the same time, so it would slow down. Now, we don't notice that with light. Why not? Because the speed of light in air is 3 times 10 to the power of 8, and the speed of light in glass is roughly 2 times 10 to the power of 8. So it's still 200 million meters per second. Not too shabby at all. It'll go straight through the glass and you wouldn't even notice that it's slowed down. However, if you now create an angle, what's going to happen is, guys, part of the light, okay, I'll give this another go, but it doesn't seem to be wanting to draw. Part of the light, nope, it really doesn't. No. Part of the light's already inside the glass. Part of it is on the outside of the glass. So what does that mean? It means part of the light is going slower and another part is going faster. That is what causes the change in direction. So from less dense to more dense, we always bend towards the normal. And from more dense to less dense, we always bend away from the normal. Okay? So here, less dense, big angle of incidence. More dense, smaller angle of refraction. Bends towards the normal. Here, we're going from more to less. The complete opposite happens. Now, what I'd like you to notice, and this is very important when it comes to total internal reflection, Pugs, you can maybe tell me here, what happens to the angle of refraction as I make the angle of incidence bigger and bigger and bigger and bigger?
Okay, I think, okay, so we're going from 90 and we're slowly going downwards. So I think it's just going to go just on the surface, I guess.
I'm just asking you to
shot.
observe the angle of refraction. What's happening to it as I make the angle of incidence bigger?
It's getting bigger and bigger and bigger.
Are they the same?
No,
they're not. Guys, the angle of incidence and the angle of reflection is the same, but the angle of incidence and the angle of refraction, when you're at an angle of any kind, is not the same. Okay, so let's keep moving on. Right, here's where I can get to explain my example. I'm sure this will allow me to draw. And indeed it does. Haha. So, beach, sea. And you get 4 friends. My awesome art, I know. Picasso, eat your heart out. He'd be proud. Not. Right. Guys, I want you to pretend these 4 people, they don't look like it, but they're holding hands. Right? That's an amazing drawing, I know. Shh. And they're running up that way. And when I say in the sea, I mean, you know, like you're just at the beach and some of them are just in the water and some of them are just outside. And they're going to run up the way. And I want you to imagine Let's just pretend they're the same fitness, same mass. It's got nothing to do with their fitness, but they're holding hands. Okay, they've finished exams, COVID's over, everybody's having a great time, and they're running along the beach. Okay, masks are gone, and we're having a good time. What do you think, Pugs? What do you think will happen? All four of them, they're running up the way. Two of them are just in the water, two of them are just in the sand, equal fitness, etc., holding hands quite tight. What do you think?
Yeah, it's going to be easier to run on the sand versus the beach. So there's going to be like the two on the left-hand side are obviously going to take a lead, right?
They are. Well done. So the two on the left, guys, will be taking the lead, and the two in behind in the sea will be kind of lagging behind. So what will happen is the guys that are on the beach will end up turning towards the sea. This is what happens. Whereas, let me just, rather than erasing my amazing guys, let's just erase the beach and the sea. All right. And whereas, let's say I now change it, and they're all going to run into the sea together, right? So they're on the beach, and now they're going to run into the sea. What's going to happen here is they will all slow down. They will all slow down together. And this is the light hitting the glass at 90. No change in direction. Speed decreases, wavelength decreases, frequency stays the same. Whereas the last example there was light hitting the glass at an angle. Speed decreases, wavelength decreases, frequency stays the same. But this time there's a change in direction, and we call that effect refraction. Okay, so let's deep dive into this. Which way does the light bend? Less dense to more dense, it always bends towards the normal, and more dense to less dense, it always bends away from the normal. Now, what the hell do we mean by that? So here you've got air and you've got water, and let's say it's going from water, which is a liquid, to air. Well, if you read the top two lines, it should bend away from the normal. In other words, it moves away from the dotted line. I don't actually understand myself why they call it bending. To me, it's just changed direction. But all books refer to it as bending. So it's went away from that dotted line. It's bending away from the normal. Whereas next, when you go from water to glass, so you're in a liquid, but this time you're going towards a solid. Solid is more dense. So if you look at those top two sentences, it'll bend towards the normal. In other words, it's going towards the dotted line as opposed to away from it. And we've got air and plastic now. Let's say you're going from the air to the plastic. You're now going from less dense to more dense. What's going to happen? It's going to bend towards the normal just like before. And finally, you're going from, let's see, water to air. You're going from a liquid to a gas. Think about it. Which one's the least dense? Pugs, I'll let you answer this one. What do you think? Towards or away this time?
It's going from more dense to less dense, so it's got to be away from the normal.
Absolutely. That is it. That is absolutely it. Now, you might go, do you not need to measure angles and stuff in exams, sir? There are times, but a lot of the times they'll say to you, sketch, draw, outline. Okay, these are just go ahead and show the examiner what happens. You don't need to be 100% accurate. But if they ask you to measure angles, of course, that changes things. And then you do need to be accurate. And we'll deal with that when we do the exam questions. Guys, now we're going to look at the next couple of formulas in refractive index. And I'm not sure, Pugs, but there's total internal reflection to come after this. It really depends on timing. That might have to wait until Thursday. But, you know, if we can get this out of the way, it's a major, major part. So what is refractive index? Well, see, guys, to you, it's just a number. And you're like, what? A number? Well, let me put this into context for you. Diamond is considered to have a large refractive index, and it's roughly 2.4. Whereas glass or plastic, glass probably, has like a lower refractive index in the region of 1.5. Now, what's the difference? If you ask a girl, she'll tell you the difference. If you ever get married when you're older and buy your wife a glass ring as opposed to a diamond ring, I don't think that's going to last very, very long. Now, why is that? You look at a diamond, it looks all shiny and glittery and sparkly and pretty, things that I just can't understand, all right? I can see it, but it doesn't relate to me. Whereas if it was glass or worse, plastic, okay, it doesn't have that shiny, glittery, sparkly edge. And what is all that to do with? It's to do with how light bends inside a dense material. Think of chandeliers, for example. You know, you go into like hotels or stuff or fancy buildings, and they've got these chandeliers, and they all look very, very sparkly. That's all to do with refractive index. So refractive index gives you an indication of how much the object in question bends the light. So here's an angle of incidence between the normal and the ray of light. I'm going to make a point about that actually. And the angle of refraction also being between the normal and the ray of light. Now, what do I mean? I mean that, guys, the normal is an imaginary construction line that we draw. We put it there, and it's got one purpose and one purpose alone, to measure angles. So what happens a lot of the time in the exam, especially if it's multiple choice, the examiner gives you A, B, all right, you know, C if you like, I'm just making stuff up now, D, and they'll say which one's the angle of incidence. The angle of incidence or refraction must always be between that dotted line and the ray of light. Because if you're not going to use it, why is it there? Okay, I'll see exam question, and they'll give you this angle, like 29 degrees. And the student will use it, and you're like, well, why are you using it? Because it's an angle that's given to me. What you need to do is 90 minus that angle. Why? Because the angle of incidence and refraction is always measured between the normal and the ray of light. Now, why do we do it that way? Because not all surfaces are flat. You know, you can have curved mirrors, curved glass. It's a nice reference point out with the glass. It's always the way we do it. All I would say to you is, if you've drawn this dotted line, but your angle is not touching it, ask yourself, well, what's the point of you being there? Okay, it's only got one point, and its purpose is to help you use a protractor and measure angles. And again, when we do the exam questions, I'll detail this. So the two formulas that you need to know, refractive index equals sine I over sine R. Okay, now in this case, sine 30 divided by sine 20 will give us 1.46 eventually, after we get 0.50 and 0.34. Now guys, horrific mistakes get made with this formula. Students are very good at doing just sine I over sine R, and they'll get 1.46. But you'll see students that won't even put in sine. They'll put 30 over 20, and you're like, why did you miss the sine? Because it's 30 over 20? No, it's sine 30 over sine 20. And the other horrendous mistake is, what happens if you're asked to find an angle? Now, let me do this for you. Now, look, we've got numbers already, and it looks like I'm going to have to go around the borders to do this. Let's pretend we are finding the angle of refraction. We know it's already 20, but let's pretend we've got I, which we've been told is 30. We know N, which we just found is 1.46. Let's pretend I'm being asked to find R. I know you've got the answer already, okay? But here's what we're going to do. And I'm sorry, I'm going to have to write in the corners here because it doesn't seem to... I've got a space here. So N equals sine I over sine R. That means sine R equals sine I, apologies, this is getting a bit tight, divided by N. So what do? We've got sine 30 over 1.46. Pugs, I don't know if you've got a calculator to hand. Can you tell me what that is?
Give me a second. Let me go grab one.
I've got one as well. I've got one. It's okay. I was just
okay. Go for it.
Sine 30 divided by 1.46. Guys, what that gives you is 0.342. And this is where it goes wrong. Students like, yes, 0.342. That's not an angle. You have just found sine R. It's a bit like saying 10x equals 0.342. Would you leave it like that? No. You'd get rid of the 10. You'd do x equals 0.342 divided by 10. So how do you do that when it comes to sine? You can't just divide it because you've got a syntax error in your calculator. The way we do that is we press Shift, Sine, Answer on our calculator, and you will get approximately 20. Slightly over, but no biggie, because the idea here is we've already got the answers. I was showing you how to work it back. And that, guys, is a mistake that is very, very often made by students that I would like you to take note of and make sure you avoid. So the bigger the refractive index, the more the light bends, like I've already told you, the kind of sparkly, if you like, it is. There's one more formula that you need to know, and that is refractive index equals speed of light in the air or speed of light in vacuum divided by speed of light in material. Or, see, the speed of light in air and vacuum, it's almost 3 times 10 to the 8. There's a slight difference, but it's so small that the word we use in physics and science in general is it's negligible. In other words, it's so small, just ignore it, okay? Now here, luckily there's no signs, there's no angles or anything. It's just a straightforward, the speed of light in air divided by speed of light in material or medium. You might hear the words used by your teacher. You know what? I'm going to go for it. Yeah, let's just explain this before we go today, guys, so we can just rattle off the exams on Thursday. What the hell is total internal reflection? Look, let's see if you can help me with this, Pugs. This black light, I know it's black, just go with me, went straight through the glass here. Now, an exam question, why did it go straight through? Well, a circle, that's really badly done. A circle can have tangents drawn to it all the way around. And if you know what a tangent is, it's basically a point that's at 90 degrees to the surface. So when I draw that ray of light, and I've got that tangent, they're both at 90. So at that point, the light's going straight through. And again, when I edit that video on the practical and share it with ZNotes, you'll see it. You'll see it straight away that the light will go straight through. However, at this side, the light's going to hit at an angle. So what does it do? We're going from more dense to less dense. Surprise, surprise, the light bends away from the normal. The angle of incidence is less than the angle of refraction. Now, Pugs, I hope you remember from last time, what will happen if I increase that angle of incidence? What will happen to the angle of refraction?
It should increase.
It should increase. Indeed, it does. So when the angle of incidence increases, the angle of refraction increases. Oh, shock. And here's the thing. Guys, if you keep increasing it, and this is so better demonstrated in a video, when you keep increasing it, there comes a point where the ray runs right along the surface. What do we call that? We will now give this special look. By the way, let me just do this with a pen. I hope it lets me draw on this. Yep, that's I. That's R. That's I. That's R. That's I. This time R is 90. But this I is now going to be given a special name. It's going to be given the name C. C standing for critical angle. Why the hell do we call that critical angle? Because if you go 1 measly degree above whatever that angle is, you will get something called total internal reflection. You have to see it to believe it. All right. This effect is used in fiber optics to have very, very fast internet. It's used in hospitals for endoscopy. That's where they stick something down your throat to have a look inside. And if you're really unlucky, somewhere else to have a look inside. Okay, they can use it to burn tumors, etc. So fiber optics is a major, major technology. I think I will explain this slide in depth, and we'll finish up with this, but there is more to it, and it's going to be nice on Thursday so I can recap this, because this is a part students find hard. Every material has its own critical angle. All right, diamonds is about 24, for example. So that what that means is any angle of incidence above 24, and you'll get total internal reflection. Another material like glass might be 45. Any angle of incidence greater than 45, and you'll get total internal reflection. Now, you don't need to know that. It's just every material has its own critical angle. All right? The key I want you to get is we start with refraction. See, people go, oh, total internal reflection, totally brand new topic. No, it's part of refraction. Okay? Angle of incidence, angle of refraction, angle of incidence, angle of refraction. Do make it big enough, and we have this ray that runs right along the surface. Now, the thing that I'm not mentioning here is we always have a weak reflected ray. How do you know that? Next time you look in a shop window, notice you can see inside the shop, you can see yourself. Depending on how you look at that shop window, sometimes you can see more of yourself than inside. If you see more of yourself, more light is reflecting. If you can see more inside the shop window, more is refracting. Why am I mentioning this? Because some exam questions won't stick this in, and others will, and then students are like, whoa, what just happened? I want you to understand sometimes you put it in and sometimes you don't, but it's always there. And what's going to happen is, guys, as that angle gets bigger, this ray, I'm sorry, that's so badly drawn. Let me just make that a bit straighter. It will start to get thicker and it'll get even, when I say thicker, I mean brighter. And then right here, right at the end, it's all total internal reflection. The thing is, some people think this thing comes out of thin air. Light hits a boundary. Part of it is refractive, part of it is reflected. It's just, why do they not show it most of the time? Because they're more interested in the fact that most of it's refracting than reflecting. It's very, very weak. That's why I kind of draw it dashed. And as we get going, it gets stronger and stronger and stronger until it all stays inside. And that effect is what we call total internal reflection. It's when the angle of incidence is greater than the critical angle for that material, which is specific to that material. I mean, we absolutely are not finished that topic, but I think for today, you know, if I was to explain the next slide, it's going to take 10 minutes on its own. So, you know, I don't know how you feel about this, Pugs, if there's any questions that need answered.
Yeah, so we can have a recap of today's topics on Thursday and then head with the past paper questions. There is one very interesting question that popped up in the comments. So why doesn't light bend when it hits the surfaces 90 degrees? Where does it go straight through?
Right. Okay. Let me show you. That is a good question. And let me explain it again. In fact, I'm going to explain it in a way that I didn't explain before. Let's just go back. Sorry, let's just end the show and go back. It'll be quicker. Discard. And let's just go to the very, very first one. I hope this will make sense to you. See, the thing is, most people think of light as a narrow, thin beam. But light's a wave, and we're not talking about that today, but when you do the rest of this topic of waves, light, and sound, you learn that light is a wave. Now, I want you to imagine looking at a sea wave coming in towards the beach. If you're quite high up and you're looking down, what will you see? Well, what you should see is a bunch of lines coming towards shore. I want you to imagine the orange thing here is the sea. I know it's got a very beachy color, but let's just call it the sea. Sorry, let's just call it the beach. My bad. We can stick to the beach. I've got that mixed up in my head. Let's call that the sea. All right, it's a beach. Now, I know water doesn't go through the beach. I want you to humor me here. So when you're looking at the sea from above, all you see is a bunch of wave fronts coming towards you. Well, that is what light is. It's a bunch of wave fronts. So why doesn't it change direction when it hits the glass at 90 degrees? Is because every part of that line, which should be straight, by the way, which I've not done a very good job at, will hit the glass at exactly the same time, meaning the wavelength becomes less, but it keeps going straight. Whereas over here, when light hits at an angle, what's going to happen is the wavefronts will come in, but then there's a part I wish I could draw straight, sorry guys, where a part of the wave is outside and a part of the wave is now inside. And the issue is when the part of the wave that's inside is going slower than the part that's outside. Whereas on the right-hand diagram, every part of that wave slows down at exactly the same time. So its result, it goes straight through. Whereas if it hits at an angle, if it hits part of it first, then the other part's just going as fast. What happens? It will change direction. Look, guys, I've got this ruler here, right? And I want you to imagine this is a meter rule. I'm just going to hold this very, very hard, not let it go. Imagine this was allowed to move. What happens? It turns. So I'm exaggerating because obviously the waves are moving, but the exaggeration here is if you don't allow that to move and you allow that to move, the natural tendency is to turn. Pugs, how do you feel about that? Is the drawings, I'm sorry,
Yep.
I need to make the line straighter.
Yeah, I think that makes a lot of sense. We've got one question more and we'll wrap it up for today. It's just that when it reaches the total internal reflection, does the width of the ray, is it same as the input, as in like the ray that comes out, the totally internal reflected ray? Is it the same as the input?
Okay. Yes,
the width of
brightness, absolutely.
brightness.
If you're talking about light intensity, okay, if it's totally internally reflected, yes, it is. That's why if you noticed, if I did the first couple of diagrams, I made the reflected ray kind of dashed. Okay, this is actually very, very well explained in my book, but I kind of made it weak. And as you make the angle of incidence bigger, that weaker reflected ray actually becomes stronger. Guys, next time you're at a river or a loch or anywhere where there's water, you'll have come across this, where you'll see paintings of a reflection of what you see in the water, and you just see a mirror image of mountains in the background. Well, if you look at the water at a different angle, you'll see more of inside than you do outside. Whereas if you look at it from an angle, you see more of outside than inside. It's all to do with how you view it. Again, look at a shop window, dead square. You'll see more into the shop than you will outside. Look at the shop window at an angle. I guarantee you see a bigger reflection than you will refraction. So what that tells you is what you're seeing is changing in strength or intensity, if you want. Okay, the proper physics term, which you don't really need at IGCSE. But yes, if you want to talk about width or intensity or brightness of the ray, the totally internally reflected ray has to be the same as the one coming in, theoretically at IG. Okay, we can deal with semantics at A level.
All right. On that note, let's wrap it up for today. Thank you all for joining in. We'll be solving problems on Thursday. We'll also do a short recap and a more deep dive into total internal reflection. For updates, you can follow the Instagram page or subscribe to our YouTube channel. Or if you want to ask more questions, you can join the Discord server for ZNotes. And thank you. See you guys again on Thursday.
Thank you very much.